I'll discuss some prospects of gravitational wave detectors and also some basic stuff about gravitational wave data analysis. So we will start with the principle of the interferometer. So for example, the LIGO interferometer. So you probably have seen the diagram many times, right? So it's a microscope interferometer. With two arms. Then you shoot a laser from this port. Well, there is another mirror here called power recycling mirror. So basically, the power of the laser is increased after passing through this mirror. And then it goes into these two cavities. And if everything is perfect, you are not supposed to detect anything on this port. Okay. So this is called the bright port. And this is called the dark port.
Why is it called dark port?
Because it's dark. There's no light coming out.
Because they try to make the interference destructive, right?
Yeah.
Okay.
So so let me label the mirrors position x1, x2, and x3, x4. So apparently this dark port signal, the readout at the dark port, is proportional to x2 minus x1, right? So it's a differential length between these two arm cavities minus x3 minus x4. So it's a function of the mirror positions. But then, of course, if gravitation waves comes in, right? So let's say H plus wave comes in, it will squeeze one cavity while pull the other cavity, right? So the signal here will be proportional to H plus. But then you have other things in addition to this signal, because, for example, the reflecting surfaces on these mirrors are not perfect. They are fluctuating because of thermal noise. So I'll explain a bit about thermal noise later. So there is a classical piece of the noise. We call it coating. Okay, or classical. And then there is another piece which comes from the fact that the light is quantum. Okay, so the quantum light will generate additional piece of noise. We call it NQ. Okay, so at the end, the readout has these three components. And basically, you want the amplitude of the signal of the gravitational wave to beat the amplitude of the combination of these two noise sources, and then you can detect the signal. Okay, so let me first explain what is a quantum noise. So basically, if you just look at a very simple problem, if you just have one mirror, and then you shoot light on the mirror, and then you want to use the light to measure the position of this mirror. Now, of course, let's say you have m photons in unit time. Okay. So intuitively, each photon should be able to measure the position of this front surface to give an accuracy. Let me call it delta x0. Okay. Then you have m photons. So the total accuracy will be delta x0 divided by square root of m. Okay. So let me call it delta x short. So this is the so-called quantum short noise. Okay. But then there is additional effect. So if you have m photon shining on this mirror, each photon will kick. Well, each photon will kick the mirror a little bit, right? So each photon will deposit a momentum delta p 0, which is roughly h mu. And because the laser, it's usually in a coherent state, so the number of this laser is not in a number eigenstate. Okay, so that means there is a fluctuation. So in a coherent state, the fluctuation on the photon number is proportional to square root of m. So that means that you will, in total, the fluctuation in the momentum kick in unit time, that's the fluctuating force. Okay, so it is del p 0 times. So it's roughly h mu square root of m. So depending on how this mirror is suspended, so if this is a free mirror, then the resulting position, position fluctuation, because you have a fluctuating force, will be delta x r. It's radiation reaction position, radiation reaction induced position. So this is basically delta p divided by m omega squared. Okay, so it's in the frequency domain. So basically you have two pieces, and this piece is called quantum short noise, and this piece, because you have a radiation pressure of the laser, is called quantum radiation pressure noise. Okay, so basically, this quantum noise is a combination of these two, and the spectral density of the quantum noise, if you combine these two, will look like something like, let me define the quantity H SQL divided by 2. So if we combine these two independent noise sources and compute the spectral density, something like this. So you can, the important thing is the k here is proportional to n. Okay. So this piece is proportional to n. This piece is proportional to 1 over n. So the piece that's proportional to n is the radiation pressure noise, because this spectral density is the noise square, right? So noise amplitude is proportional to square root n. The power is proportional to n. So this is radiation pressure. And the one piece that's proportional to 1 over m is the short noise. Okay, so you have this very simple form. And then you can quickly see that because I have this bracket and we have a constant here, so this thing is minimized when this k is equal to 1. Okay. So if you want to draw this, the frequency dependent of these two pieces, so you will find that here it's dominated by the radiation pressure piece. Here it's dominated by the short noise piece. Okay. And they equal when they touch this line, which is the H square SQL, which is a frequency dependent quantity. So they usually call this quantity, let me explicitly write down, H SQL is square root of 8 H bar and omega square L square. So they usually call this quantity as the so-called standard quantum limit, because that's basically the minimum of the quantum noise. Okay, so it's a quantum limit, so you can adjust the power of a laser such that the total quantum noise can reach this so-called standard quantum limit. Okay. So basically, if you look at the LIGO detectors at higher frequencies, it's dominated by the short noise. Okay. So there is another interesting fact. Okay, so so this is roughly 10 to the minus 25 square root hertz. So if you have a 200 kilogram mass, and if you're looking at 100 hertz in frequency, and the cavity length is 20 kilometers. LIGO, the cavity length is 4 kilometers, but in the future we may build detectors which have longer arm lengths. Okay. So there is another interesting fact about this standard quantum limit. So if you have a harmonic oscillator, with frequency omega. And you want to, and let's say the harmonic oscillator is in its ground state. Then the ground state fluctuation of its position, x, q, should just be equal to square root of h bar over m omega. Okay. This is a 0-point fluctuation of a harmonic oscillator. And then if you want to compare this xq with this hsql, then you will find that basically this is hsql times the arm length, then divided by this factor. So what does this mean? This means that if we adjust the laser power in the cavity such that the quantum noise is minimized, then we have already reached the precision that we can probe the 0-point fluctuation of the test mass. Okay, so in other words, because it's already the operating region in the advanced LIGO. So in other words, the interferometers, the gravitational wave detectors, are operating in the quantum region that it's already probing the 0-point fluctuation of the test mass. Okay? That's why it is a quantum device. Okay, so this is the quantum noise. And the second most important piece of noise in the detection band of LIGO is the coating noise, or coating thermal noise. So each mirror, you have coatings, and the coatings will fluctuate, and that will generate fluctuating noise. Okay, so schematically, let me draw one mirror here, and let's suppose that we shine this laser with the so this is direction in the horizontal plane, x and y. So it's a 2D plane, and this Gaussian wave packet has a profile in this horizontal directions. So let me call it u0 x. So let's assume that this surface is, well, it's fluctuating in time, and the vertical position of the surface C is a function of x. Okay, so it's x and y. Okay, so basically, this laser shines on this surface, which is not perfect, and then you will see a reflected wave. Let me call you out. So basically, u out as a function of x should be just u0 x times e to the 2 e to the I 2 k0 c. Well, k0 is the wave number of the laser. And the complex reflectivity of the mirror as a whole is basically U out times U0 star X. Okay, so you can plug in here. Basically, the fluctuating mirror surface will generate a fluctuation in the reflectivity function, which is 2I A0 dx I x divided by Ix. Okay, so that's the quantity to be measured, the fluctuation in the reflectivity. And here the I is the intensity function, which is basically U0 square. So let me call this as 2I K0 C. Okay, so the C is so the laser beam measures the averaged C. Okay, right? So it's averaged by the intensity profile of this laser. And then we can ask the question that what makes this deformation of the mirror surface? So by doing that, for example, we can divide this mirror to many layers. For example, we already have a coating layer, and then we have the substrate, which is a crystal. We can also divide it by many layers. So especially for this coating, it turns out that the loss in the coating is very big because it's not, so the substrate is crystal, the quality factor of the coating is very low. Okay, the Q coating is much less than the Q substrate. So basically, this Q means that if I just have the coating and if I bend the coating, the Q factor is basically how many cycles this coating will oscillate before it dissipates all this initial elastic energy. Okay, this is a quality factor. Coating of the coating quality factor is much smaller than the substrate. So in thermodynamics, there is a famous theorem called fluctuation dissipation theorem. So basically, it says that if I have oscillator connecting to a heat bath, and there is a heat bath or dissipative source, then it should feel a fluctuating force. Okay, the fluctuating force, the spectral density of the fluctuating force should be proportional to the resistance, effective resistance, and kVt. Have you guys learned fluctuation dissipation theorem before? No? So it's a very classical theorem, and basically the essence of the fluctuation dissipation theorem tells you that whenever you have a lossy system, okay, whenever there is loss, there is also a fluctuation force, and the loss will be proportional to the spectrum of the fluctuating force. Okay, so will be the dissipation, and this will be the fluctuation. There is a simple proof. You can just imagine there is a harmonic oscillator, and then you connect with additional bars, and then you can easily show this theorem. So now you have this relation between the loss and the fluctuation, and then we know that the loss in the coatings is much greater than the substrate, which means that there is a fluctuating thermal force in the coating layer, which is much greater than the fluctuating force in the substrate. So the F here in the coating, which is up and down, or it could even have force in the transverse directions. It's much bigger than any fluctuating force in the substrate. And this force in the coating, because coating is attached to the substrate, then it will try to bend the substrate. Okay, there is a force, and then it will try to bend the substrate, and this bending just creates basically that's the dominant piece of this vertical displacement of the front surface. Okay. So if you solve the elasticity problem, so you apply a randomized force on this surface, on the coating surface, and this is an elastic problem, right? You can assume the Young's modulus of the substrate, and you have a force, and then you can basically compute how this whole thing is deformed, and then you can compute the spatial profile of this. Okay. So at the end, the spectral density of this C average, okay, so then you average over the beam profile, is roughly something like so L here is the thickness of the coating. This phi, people call it loss angle. It's basically roughly proportional to 1 over the quality factor. Okay. And this is Young's modulus of the substrate, and this A effective is basically the beam size of the laser, so it's defined as okay. So the physical meaning of this thing is very clear. So according to the fluctuation dissipation theorem, the spectral density of the fluctuating force is proportional to kBt. That's why there is a kBt. And its proportional to the loss. Okay, so it's proportional to the loss, which is proportional to 1 over quality factor. And because it's a force, I want to compute the displacement. Then, I mean, the displacement is basically force over Young's modulus. The softer the substrate is, and the more bending there will be, right? So it's inverse proportion to that, and then it's averaged over the beam profile, because it's it's a beam averaged quantity. So basically, if you want to improve this noise, you can either try to make a larger beam, right? So you can increase the bins. So people have been talking about because usually in the cavity they're using the fundamental Gaussian mode of the laser. They've been talking about using higher order Hermitian Gaussian mode in the cavities, such that you can increase the beam area. So you can increase that, or you can try to increase decrease this loss. So if you find better coating materials with higher quality factors, this will also be this will also decrease. Okay. So if you look at a usual sensitivity curve of LIGO, so this coating noise will be one of the most dominant part in this whole detection band of LIGO, right? So this will be roughly 100 Hertz. So it's very important. Although the coating itself is very small, it's very important in gravitational wave detection. Okay, so this is a quantum short noise. You may ask whether this is the radiation pressure noise or not. It turns out that for LIGO, this is not dominated by the radiation pressure noise. The radiation pressure is something like this, but it's smaller, so it's dominated by other classical noise sources, which we will skip, I guess, today. So it's coming from the gravitational interaction with the seismic waves and the suspension system. Okay. Any questions so far? Okay, so these are the two main noise sources of LIGO. So we now have a better understanding of the detector. So let's try to discuss a bit about the data analysis aspect for gravitational wave detection. Okay. So you may have heard the word matched filter many times. When people give LIGO talks. So I'll try to explain what this is. This is the main technique for detecting these compact, like binary black holes and neutron star systems. Okay. So, let's suppose that the readout is Let me call it xt, is the noise nt, which is we just explained there is the classical piece, the quantum piece, plus h. So this is your waveform, right? In the time domain, the waveform is like something like this, yeah, for binary black holes. So this is the arriving time of your waveform. So the matched filter is a method that I compute a quantity called c tau, which is basically the correlation function of the readout with a filter function. Let me call it q here. Okay, so it's very simple. I just multiply the data with a filter function with a constant, with an offset, and I change the offset. Right? So and then I have this correlation function. Of course, in the frequency domain, this is plus infinity to minus infinity. The frequency domain f times the frequency domain filter okay.
Sorry, what is this filter function?
Yeah, so right now it's just arbitrary function. Okay. So then we will discuss how to choose this filter function. Okay, so now we have this product. And then we can plug in the expression for x. So now the C has two components. C will be n tilde f q star f. I've not done anything yet. I'm just plugging in the signal. So now it has the C contains two parts. The first part, because n is a noise, so this part has zero average. So if you average over the ensemble of noise, so the average equals 0. But then this part is the signal, is a gravitational wave signal. So this function times this function in general is non-zero. So let me call it C average. Okay. So basically, the average of this correlation function is this piece, and it's a constant signal. But this piece, although the average is 0, this is noise, so it contributes to a fluctuating piece in C. Okay. So so you can compute the fluctuating piece, the variance of C. it's basically so you have n tilde f tilde star f prime q star f q f prime e to the minus I to pi I f minus f prime tau. Okay, so this will be the variance. So these pieces are all basically constant functions. So the ensemble average will just act on this, on the noise piece. And in the frequency domain, it is just equal to the spectral density times the delta function. Okay, so you can plug this in, and then this will equal to, basically is the spectral density SNF times QF squared dF. Okay, so I've defined this correlation operation. I define the operator and obtain this quantity C, and which has two pieces, a constant piece and a noise piece, and I just compute the variance of the noise. So the signal to noise ratio is basically the ratio between these two pieces. Okay. Okay, so in principle, we want to maximize this guy, right? For a given noise level, we always want to maximize the signal part. So we want to maximize this so-called signal to noise ratio. And of course, this signal to noise ratio depends on the filter function Q, because all other things are already fixed, but we can freely choose the filter function Q here. So then it's a question that how do we choose the optimized filter function Q? So in order to find the optimized filter function, we can define an inner product. So this inner product is very handy in computing the various quantities when you want to compute SNRs and other things. So the inner product between two functions A and B is just the product between A tilde and B star. Okay. So it's basically the inner product of these two quantity weighted average by the 1 over the spectral density of the detector. So using this inner product, then this SNR, the signal to noise ratio, is basically H e to the 2I F Sn times Q divided by Sn times Q. So it's in this very simple form. So if we want to maximize this quantity, we can imagine that there is a vector space of all functions, right? So there is already a function like this, basically it's h. But then we're trying to find another function such that the inner product between this function and h is maximized. This is just a normalization, right? So you have a unit vector, but then you want to have this unit vector to maximally overlap with this thing. So of course, then so basically you take variations over all possible function q. You want this to be 0. Of course, the solution is that the q has to be proportional to, say, some constant times h tilde. Right, so it has to be proportional to h tilde over Sn. So now this is an optimized filter function we can apply to a data stream that maximizes the signal to noise ratio. And this optimized filter function is basically proportional to the waveform itself. So we can plug in this optimized filter function back into the definition of SNR. So the maximum XNR we can extract from the data, or then we call it optimized. So if we plug this in, it will just be equal to H, the inner product between H and itself. Okay, so this is just 2 times. So you have been asked to compute the waveform of a compact binary in the inspired stage. Basically, you know how to compute the H. Okay, so then after obtaining this H, then you can say, for a given detector, let's say advanced LIGO Hanford, and then you can just insert the spectral density of that particular detector, and then you can obtain the SNR of that detector for that given event. Okay, so basically this is the formula to compute the SNR for any gravitational wave event. Okay. I have something else, but we only have 10 minutes, so probably I will not talk about that. probably this is a good point to stop. Yeah. Okay. Any questions? Yeah.
I have one. It's not about this, just an idea.
Yeah.
What do you think about people doing research on trying to use Bose-Einstein condensates as gravitational wave detectors?
So people have been thinking about how to build a very high frequency gravitational wave detector. So for LIGO, it only works in the 100 hertz or maximally up to kilohertz band. This is a band for astrophysical sources, but higher than that, there are very few astrophysical sources that will generate, let's say, megahertz or higher frequency gravitational waves. The only possible source is probably from early universe, the primordial gravitational waves. So people have been thinking about, if I want to detect these primordial gravitational waves, how do I do it? So when the wavelength is small, you don't need to build very long detectors, because if the arm length is longer, let's say, than the wavelength, then it will, right? So this it's basically the arm length is wasted, because then it will there is a positive return and negative return and positive return, right? So the optimal length is probably equal to wavelength, half of wavelength, something like that. So the good thing is you don't need very long detectors. You can build small detectors. And then people have been thinking about, maybe I can build a small interferometer, like the microinterferometer similar to LIGO. Or I can use some other material. For example, in the early days, people have thought about just have a resonant bar. And that's the first generation detector, is a bar detector. So I can use a resonant bar, and I can still try to use that to detect gravitational waves. Or you can try some other resonators. It doesn't have to be an elastic bar. It can be liquid, like say liquid helium, or it can be Bose-Einstein condensates. So as far as I know, the Bose-Einstein condensate idea, it's very difficult to get a very good performance. So if you want to increase the sensitivity for that case, you probably need to use very high squeezing. So by squeezing, I mean when we talk about for example, when we talk about the quantum noise, we have assumed that the quantum state of laser is basically a perfect circle in. So if you have learned quantum optics, so it's like an oscillator. You have X and P, so it's a perfect sphere. So no matter what direction you measure, the combination of XP and the variance is the same. But then there are techniques that allows you to squeeze the variation in one, they call it quadrature, and extend the other quadrature. And then if one dimension is squeezed, and that means the quantum fluctuation in that dimension is squeezed. So they want to use the same technique for the Bose-Einstein condensate, and the squeezing level required is, I would say, it's beyond, I don't know. It's a future technology, probably in 100, 500 years. I don't know. So yeah. So currently, advanced LIGO have been. Geo has been testing some squeezing technique for future detectors. It's successful, and I think for in the future we're definitely using squeezing techniques, and then the magnitude of squeezing is what they call it. So it's like 10 dB or so. But I think for this Bose-Einstein condensate idea, they need 1,000 times or even higher squeeze it. So it's too difficult, if not possible. Yeah. Okay.